Hello everyone. In this video, let us try to talk a little bit more about the hold analysis with single clock and the impact of clock tree on the hold timing checks. So we said that how the addition of buffers in the capture clock path could be disastrous. So we can so when we add a delay, when we add a buffer of, let's say, delay x and keep on adding that, this directly impacts the right hand side of the equation of the data required, that is the data required time, and the data required time becomes more and more stringent. The requirement becomes more and more stringent, and it actually becomes difficult for the data arrival time to catch up with the data required time if we keep on adding buffers in the capture flop clock path. This essentially means that if we do not maintain a zero skew, we are in problem. So we have seen examples in the hold timing analysis, we have seen examples in the setup timing analysis, that if we maintain a zero skew, if we do not maintain a zero skew, things are slightly going to be things are not going to be in place. There will be problems like you might get the data required time is very high, and that will result into hold violations because data arrival time might just not be able to catch up with the data required time. And in the other case where we had in the setup timing analysis, where we had kept on adding buffers in the launch flop clock path, again the data arrival time becomes so huge that it might that the data required time might not catch up with the data arrival time. So you might want to look into those videos as well. So there are problems if we don't maintain a zero skew in the clock tree that we have built. So that's why when we started with these lectures, we always emphasized on a zero skew clock tree network. But there are there are ways in which the clock tree is built based on the setup and hold time slack. So there are ways where we can build these kind of trees as well. These are like the advanced techniques that has been used to build the clock tree. So that part will be a part of a quiz. So maybe the quiz will be something like this. It will be asking you to build a tree based on the slack that we have for the setup and hold time. So we will be putting that part as a part of the quiz, so that you will rack your brains and get to the solution of how to build a tree when you have let's say 10 picosecond setup violation and negative 20 picoseconds as hold violation. In that case, how will you build a tree? It's basically slack based tree. We call it a slack based tree. So this will be put as a part of the quiz, and for that to clear that quiz, you have to go through these videos so that you understand what the skew is and what a slack is, what data required time, what data arrival time is all about. So before entering that quiz, maybe go through these videos, and it will be fairly simple to solve the quiz. So this was the last slide that we had in the clock tree synthesis set of videos that we have started with, and we think we have successfully completed we have successfully touched all the topics of the clock tree synthesis. With respect to clock tree synthesis, there will be few items here and there which we might put as a quiz, because this will be related to what we have learned till now. That will fairly cover the clock tree synthesis topic. So let's try to revise, or let's try to summarize what we have learned in this set of videos. So we started with the clock tree quality checks. So what we did was we identified certain parameters and said that those parameters will be the quality check parameters of the clock tree that we are building. So whatever we build, there should be some way to quantify it. So this particular set of checks was one of the way to quantify the clock tree synthesis, clock tree that we have built. So there were skew power. It was skew power, latency, crosstalk, and pulse width, all and duty cycle. We came up with the list and tried to quantify and try to first identify the quality check parameters, because if we don't identify the quality check parameters in the very beginning, then there will be no way to qualify the tree that we have built, to justify the H tree or whatever tree we have built. There is no way to qualify that particular tree. So that's why in the beginning we started with the quality check parameters. Next we did was we built a local H tree. We came up with a very plain algorithm, very simple algorithm, that's a clock tree, to build a clock tree, which was called as the H tree, and it was only for a 16 clock endpoint. We have built a tree only for a 16 clock endpoint. So that tree basically helped us to understand how does the quality check varies, and what are the how to measure the quality check of any particular clock tree. So this particular simple tree helped us to understand the quality check parameters in a practical situation. Basically, this tree was built on a chip. We took a chip of 16 clock endpoints and built a tree on that, and then did the quality check of the H tree. So these three were pretty much related, and we identified problems when we did a quality check of the H tree and came up with a solution called as clock tree buffering. So buffering has actually helped us to reduce the max capacitance and max transitions of the wires of the nets, because we identified a problem that the nets were too long, the wire RCs were too long, and there is a solution to solve that. And the clock tree buffering also, we learned that at what points, at what exact points you need to put the clock buffer to get a very decent slew which is power aware and which is also skew aware. So we came up with all those solutions in the clock tree buffering technique. Next, we looked into a buffered H tree. So after we learned the concepts of clock tree buffering, we have taken the H tree that we have built over here and buffered it, and we did a buffered H tree. And again, with the buffered H tree, we did all the quality checks. Basically, we checked for skew, we checked for power, we checked for latency, and also we and in this section also we came up with an optimized clock tree, where we have mentioned that we should not be over designing any circuit. We should be using only limited number of buffers that is required for the clock, that is sufficient for the clock tree. So this was pretty much power aware. We have reduced the we were able to reduce the short circuit power and the switching power to some extent, even the leakage power to some extent. So we did all those in the buffered H tree topic. After we were clear with the basic topics of the clock tree, we went into a more advanced topic, which was like H tree for an uneven spread of flops. So these H trees were for a 16 clock endpoint, which were very evenly spread, which were very periodically spread. So we took a problem where the flops were very unevenly spread, and tried to build a tree for the same. So the algorithm, the basic concept still remained the same, but only the algorithm changed a bit. It was derived out of the basic algorithm, but only the routes, the way the routes were made, those were differed. So yeah, we have covered that part as well, and we also looked at how does this skew and all the quality check parameters with this kind of clock tree, how were they met and how good they were. So we looked into all those topics also. Next, after looking for a 16, after completing the 16 clock endpoint clock tree, we moved ahead and built a tree for a millions of flops. We looked into the strategy of building a clock tree for if there would have been millions of flops. So we looked into that strategy, and the strategy was pretty simple if we actually look, because we were already aware of the concepts that we have learned in the first 6 to 7 topics, and then we came up to building a tree for millions of flops. So the strategy was pretty simple. It was again a tree, but it was building a tree for small subtrees, and the subtree was built using one of the above techniques. So it was pretty simple. It looked very complicated, but it was pretty simple to build a tree for even the millions of flops. Next, after we did all this, we were much more power aware, because we were claiming that the 70% of the power that has been consumed by a chip is consumed by the clock tree. The clock tree itself consumes like 70 to 75% of power. So there should be a technique to reduce it, and we came up with a clock gating technique which helped us to reduce the power almost by half. We saw how the clock gating technique helped us to reduce the amount of power significantly while maintaining the skew. So when we actually built a tree with the clock gating cells, there was a skew problem, there was a skew issue, and we have looked into techniques how to maintain the skew while we use clock gating techniques as well. So this was a pretty interesting topic that we have covered in this section, and which was too much conceptual, and this was the topic where we introduced a lot of timing concepts, like delay tables and all those things. We looked into all those in this section, so this was pretty interesting. Next, we did us and the last we did a very brief static timing analysis. We did a setup timing analysis and hold timing analysis with the clock tree that we have built. So the purpose of the static timing analysis of in this particular section was to show you the impact of clock tree on a timing on a setup and hold timing. So that was the intention that we have introduced the static timing analysis part in the clock tree itself, because clock plays a major role in your timing, basically timing and power. So power we have covered in this topic, and timing we have covered in this topic. So we have seen the impact of uneven skew clock tree. What is the impact of uneven skew clock tree on a timing, and how bad it can go, how disastrous it could be if you don't try to maintain a zero skew clock tree network. So we have looked into all this, and that was because static timing analysis by itself is a very huge topic. and it needs a lot of details and a lot of explanations, but we were able to briefly cover the impact of clock tree on static timing analysis. So this is what I had on on the clock tree synthesis videos. Next we will be coming up with videos on crosstalk noise and coupling capacitance, which was one of the part of the checklist, but we said that this will need a huge amount of discussion, so we kept this topic as a separate set. But there will be around 40-45 videos that will be uploaded on this particular topic, which is crosstalk noise and coupling capacitance. This is also very important topic because this is the thing that the recent VLSI industries are looking into. VLSI engineers, when they actually go for hiring, they look for all these concepts, including the including the clock tree synthesis concepts. They're looking for concepts of crosstalk noise and coupling capacitance. So we have plans to bring up that particular topics in a separate set of videos. Then we will be looking into static timing analysis. We are already having videos on static timing analysis, like 45 to 50 videos on static timing analysis, which will be coming up with very soon. And this will be helping us to cover all the basic timing concepts, including non-linear delay model that has been we will be using the basic non-linear delay model for static timing analysis, and will be understanding we will be understanding all topics, all aspects of timing in this particular videos. And finally, this would be an advanced lectures on composite current source based static timing analysis. So NLDM, the non-linear delay model, had been used for a pretty long time to model any logic cell or any gate. But recently VLSI engineers have came up with this particular concept of composite current source, where they actually charge the output capacitance and try to construct a waveform out of it. So this is a different technique, and based on that technique we will be doing an STA. So there are a couple of videos on this topic as well, and we will be coming up with this one, but this will be only for advanced engineers, advanced VLSI engineers. So for the basic ones, the crosstalk noise, coupling capacitance, STA and the CTS, this will pretty much cover all of them. So we have plans for CCS based STA, but only for advanced topics. Okay. And in case of any queries related to crosstalk noise, coupling capacitance, clock tree synthesis, static timing analysis, you can get connected to me at vsg@vlsisystemdesign.com. And thanks a lot for watching into these videos, and we hope that the approach that we have taken to solve the problems in the clock tree synthesis videos, hopefully the same approach or even a better one would be taken by you to enhance the skills in VLSI career. Best wishes and thanks a lot again. Thank you.